All right. So we were most of the way into 6.1 and 6.2. We were kind of actually done with section 6.1 and starting section 6.2 of the book. We dealt with the cosine and sine functions. Cosine and sine give us x and y values on the unit circle, but because as we go around the unit circle, we have this oscillating pattern. When I graph cosine of x in the xy coordinate grid, so the input is the angle, the output is cosine of that angle, I get this nice wave pattern. And sine of x, I got a nice wave pattern. Both of these functions had repeating patterns, which means they have a period. We transformed those and saw how that affected the cosine and sine function. Found some zeros. Oh. And all that kind of good stuff. Now, before I move on, I did want to mention something. Again, we'll use it in just a moment. But when we graphed cosine of x, f of x equals cosine of x was an even function, right? Everybody remember that? Cosine of x was an even function, and sine of x was an odd function. Actually, I used a cheat, didn't I? So we had cosine was even, sine was odd. And we saw that with the graph. I wanted to mention that because that's also an identity. That's an even odd identity. What we mean by that, since f even means when I plug in a negative x, I get the same thing as if I plug in a positive x. And what that means in this case is that cosine of x is the same thing as cosine of negative x. Right? And sine being odd means that if you plug in a negative x into the function, you get the opposite of what you get by plugging in a positive x. So sine of negative x is equal to negative sine of x. Okay. If you look at your trig identity sheet that I handed out or that's posted online, that's like the fourth identities thing. There's tangent as well. We'll get to tangent in just a second. But these are the even odd identities for sine and cosine. I didn't mention that explicitly last time, so I wanted to mention that this time. Okay. So since cosine is an even function, we get what we call the even identity for cosine. Plugging in negative, same thing as plugging in positives. And we get the odd identity for sine. Plugging in a negative gives me the opposite of what I get when I plug in a positive. So now that we've graphed a bunch of different sine and cosine functions. Now we're going to look at the other 4 trig functions. Tangent, cotangent, secant, and cosecant. Now remember these relations. Tangent is just sine over cosine. Cotangent is just cosine over sine. Secant is 1 over cosine. Cosecant is 1 over sine. These are the reciprocal and quotient identities, right? So we've seen that before. Or we've seen those before. And this is going to have ramifications on the graph. Think about what happens when we have zeros for cosine. When we have zeros for cosine, then I'm going to get a 0 in the denominator of the secant and a 0 in the denominator of the tangent. When I have zeros for sine, I'm going to get a 0 in the denominator for cosecant and a 0 in the denominator for cotangent. Okay. So these 4 other trig function graphs are going to have asymptotes. Those asymptotes are going to happen when those denominators are 0. Okay. Now, another question that comes up is where are these functions periodic, or how are they periodic? So let's do a little bit of investigation about periodic functions and how they work. Okay. We're going to assume f and g are periodic. So assume that the functions we're given are periodic. I want to figure out, is f plus g periodic? And then is a constant times f periodic? Is f times g periodic? And then is just want you to think through this for a second. We're not going to spend a lot of time here, but I want you to think through it. Is f plus g periodic? Well, think about what f being periodic means. F being periodic means that if I add the period of f, which I'll call p sub f, then I get f of x, right? G being periodic means that if I add period of g, I get back g of x. Okay. What if these are 2 different numbers? What if this one were like 3 and this one were like 4.8? . So is this one periodic? Well, if these periods are the same, then it's definitely going to be periodic. Okay. If periods are the same, if markers are going bad. All right. So if the periods are the same, we're good to go. It's periodic. Okay. It gets a little bit more complicated if the periods are not the same. If periods aren't the same, like I said, then it gets a little bit more complicated. Imagine one period is 3 and the other is 4.8. In that case, I could create a period that works. In fact, let's do this. If one of the periods is 3 and the other is 4.8, then a period of 48 would work for both functions. Does that make sense? Because 48 is divisible by 3 and 48 is divisible by 4.8. Makes sense. Right? So as long as we have evenly divisible things, we can create some period that works. All right. It gets a little bit trickier if one period is 4.8 and the other is pi. If one number is irrational, then it gets a little bit trickier. But if both periods are the same, then definitely the two functions, the sum of the two functions are periodic. If they're not the same, then it gets a lot more complicated. Everybody follow that? So, if not the same, is all right, that's all I want you to know for right now. So if the periods are the same, adding them up, there you go. Or if the two functions have a same period, if two functions have a same period, then we can do this. All right. I'll just write it that way. Maybe I shouldn't say are the same. I should say if the functions have a common period. Like in the example I did, 48 was a common period to both fundamental period of 3 and fundamental period of 4.8. If they don't have a common period, then we're not good. Does that make sense? That's what I'll say. So if the functions have a common period, then f plus g is periodic. Otherwise, not. I'll write that one. How about a constant times f? Well, the constant's not going to change anything. If I have f who has period p, I can just apply that rule of periodic functions. So any constant times f is going to be periodic as well, right? Okay, follows that? So if I have a constant number times a periodic function, the result is going to be a periodic function as well.
Okay.
So think about like sine versus 3 times sine. Both of those are going to be periodic. All right. When you multiply two functions together, it's kind of working the same as our first. If we have a common period, common period. Right, remember what multiplication of functions gives you? When you multiply two functions together, you get f of the argument times g of that same argument. I'll write it here. That's going to be f of x because x has period p times g of x because g has period p. That's f times g of x. Okay. If they don't have a common period, then things get more complicated. But if they have a common period, then the product is also periodic. If they don't have a common period, they're not going to. And the same is true when we divide. So I wanted to start with the first one. So you can kind of see how it works, but hopefully we see how all of these works. If they have a common period, then that's true. Okay. So when our two functions can have a common period, Then we know the product is going to be periodic. We know the sum is going to be periodic. We know that the division is going to be periodic. Okay. But like in the case where one of them has fundamental period of 3 and the other has fundamental period of 4.8, the sum might have a different period than the fundamental period of the first two individual. Does that make sense? Like the period may be 48, where the individual periods, fundamental periods, are not 48 themselves. That's going to work the same when we divide, or when we multiply, or when we do anything else. Okay, so the fundamental period does not have to be the fundamental period of one of the functions. Now, that's sort of the aside that we wanted to look at, because we're thinking of our trig functions like tangent, secant, cotangent, cosecant as being made up from dividing functions I already have established are periodic. We've already established that sine and cosine are periodic. Therefore, when we take sine over cosine, since both of them share a period, common period, sine over cosine is also going to be periodic. So tangent's going to be periodic. One is a constant divided by a number. Constant function is also periodic. So 1 is periodic. Divided by cosine, which is periodic. So secant's going to be periodic as well. So we're going to have these repeating patterns over and over and over again when we graph our other trig functions. And so this is what they look like. So we should have expected repeating patterns because of the fact that sine and cosine are periodic and they share a period of 2 pi. So they share a period of 2 pi, so we should expect periodic functions. So we get tangent and cotangent. These are the graphs of tangent and cotangent. Let me graph that on Desmos just for a second. So there it is. Let me see if I can do step by pi. Okay. I'm going to step by pi so we can see this. Actually, step by pi over 2. There we go. So we can see this. Notice that these are a lot of squiggly lines. There's a lot of asymptotes there. At every odd times pi divided by 2, there's an asymptote. That should make sense because, like we said, tangent can be thought of as sine over cosine, and the zeros of cosine are pi over 2, 3 pi over 2, 5 pi over 2, et cetera, et cetera. Okay. And also notice where it crosses the x-axis. It crosses the x-axis, so it has zeros at negative pi, 0, pi, 2 pi, et cetera, et cetera. Those are all the zeros of sine. So tangent has the same zeros as sine, but it has asymptotes at the zeros of the cosine. And it'll work in reverse with cotangent. If I do cotangent of x, this has asymptotes at negative pi, 0, pi, 2 pi. And it hits the x-axis at pi over 2, 3 pi over 2, 5 pi over 2, any odd number pi divided by 2. Odd integer times pi divided by 2. Okay. Notice that the range here goes from negative infinity to positive infinity on both. On both the tangent and the cotangent, we have ranges of negative infinity to positive infinity. The domain is everything except for where the asymptotes are. So the domain, everything except for where the asymptotes are. So all real numbers other than the asymptotes, other than when the denominator is 0. Okay. Also, I want to point out that the period was pi for each of these. The domain is not the entirety of the real numbers. Like I said, it's all the real numbers except for the asymptotes. So except for when the denominator is 0. The range is from negative infinity to positive infinity. But it's kind of weird that tangent and cotangent have a period of pi, because cosine and sine had periods of 2 pi each, right? So the fundamental period when I divided those changed to pi. Weirdly enough. Okay. That kind of makes sense or no? If you think about it in terms of the unit circle, if we're tracking our point around the unit circle, while sine is going to oscillate, tangent is going to give you the ratio. And it turns out, when you talk about the ratio of your ordered pair versus this ordered pair, these are the same ratios. Okay, this one's going to be positive over positive. This one's going to be negative over negative. Negative over negative is going to cancel each other out. So that's why we only have pi. Does that make sense? So as you go around the circle once, let's take the right half of the circle. All of those ratios for tangent will be repeated on the left half of the circle. So that's why we only need a half of the circle basically to give us our period. We get that. Hopefully that makes sense. If it doesn't, that's all right. Just know that the period of tangent is pi, and it has to do with tracing around the unit circle. That is, the period for tangent and cotangent is pi. Okay. And like I said, zeros of the functions are going to happen when the numerator is 0. When I think about tangent, I think about it as sine over cosine. So the numerator is going to be the sine in that case. The denominator is going to be the cosine with tangent. With cotangent, it's the reverse. The numerator is going to be the cosine, and the denominator is going to be the sine. So zeros when the numerator is 0, asymptotes when the denominator is 0. Also, because sine is odd and cosine is even, if you think about plugging in a negative into tangent, that is going to be sine of negative x divided by cosine of positive x. We know that sine is odd. So what's going to happen in the numerator is I'm going to get the negative of sine of positive x. In the denominator, whoops, I was one step too far. And the denominator, since cosine is even, it'll just eat that negative sign on the inside. That makes sense. That sign on the inside will go away. And now I just have negative sine over cosine, which is the same thing as negative tangent of x. So tangent is an odd function as well, because it's a ratio of 1 odd divided by 1 even. Cotangent will also be an odd function for the same reason, just flip the ratio upside down. So tangent is an odd function, cotangent is also an odd function. And if you look at the graphs, or if you look back at the graphs, we could have seen that graphically by saying that it's symmetric about the origin. Both of these functions are symmetric about the origin. Okay. And then just like with cosine and sine, we can transform either tangent or cotangent. I'm just going to do the tangent one right now. But you could have also done the exact same thing with cotangent. Okay. If I multiply outside by capital A, and then take tangent of b times x minus c, and then plus d, just like we had with cosine and sine, A is a vertical stretch. Because we go from negative infinity to positive infinity, there's no amplitude here, or amplitude does not exist, because we go up forever, down forever. Sometimes people will say the amplitude is infinite as well. It's another way to say it. I say amplitude does not exist. Book says does not exist. Other people might say amplitude is infinite. B is our horizontal shrink or stretch. Because tangent and cotangent both have periods of pi, our base tangent, base cotangent have periods of pi. If I shrink or stretch horizontally, then the period changes to pi over absolute value of b. C over b is the horizontal shift. also called the phase shift. D is the vertical shift. So just like we did with cosine and sine, we can do that to tangent. And then you can do the same thing with cotangent as well. But just realize the period now is starting at pi, not 2 pi. So we'll take a couple of functions and we'll do the following. We'll do the amplitude, period, phase shift for these functions. And then we will also, for the exact same functions, find the x-intercepts and the asymptotes between 0 and 2 pi. All right. So we'll do that all at once rather than two different things. So we have f of x is equal to -2 times the tangent of 3x. And then g of x is equal to 4 times the cotangent of x over 2 minus 3. So we'll find the amplitude, the period, the phase shift. Neither of these have vertical shifts, so we're good. And then we'll find x-intercepts and asymptotes between 0 and 2 pi. Minus 4. All right. Amplitude of tangent is a deity, does not exist. Remember, tangent goes from infinity, negative infinity to positive infinity. So amplitude doesn't exist there. Okay. The period of this function, well, the period of tangent is pi, so all we have to do is take pi over 3. So period is pi over 3. There is 0 horizontal shift. There's also 0 vertical shift. I want to write that. There is a stretch vertically. Technically, it's a flip and a stretch because it's -2. So there is a stretch vertically by a factor of 2, and then a flip across the x-axis. There's a shrink horizontally by a factor of 3. That's what changed our period. There we go. Now, if I want to find zeros, first thing I would do is I divide both sides by -2. Dividing both sides by -2 gives me 0 is equal to the tangent of 3x. And here's where we have to understand what tangent does. I get zeros when the numerator is equal to 0. So I get zeros where sine of 3x is equal to 0. Remember back from last class, sine is 0 at negative pi, 0, pi, 2 pi, 3 pi, et cetera, et cetera, et cetera. So that means 3x is equal to, I'll just do it this way, negative pi, 0, pi, 2 pi, 3 pi, et cetera, et cetera, et cetera. And then I divide everything by 3. I want all the zeros for x values between 0 and 2 pi instead. Forgot, was that equal to or not equal to? I can't remember if I had the equal to or not equal to on the slide. Had the equal to on it. Sorry, there we go. So I'm just going to keep going until I hit 2 pi. Does that make sense? Or at least get 2 pi. That'd be 3 pi over 3. 4 pi over 3. 5 pi over 3. 6 pi over 3. And then 7 pi over 3. The ones between 0 and 2 pi, including 0 and 2 pi, are those. So the zeros of the tangent function, at least the ones between 0 and 2 pi, are 0, pi over 3, 2 pi over 3, pi, 4 pi over 3, 5 pi over 3, and then 2 pi. Does that make sense? Where I'm getting those from? Okay. I'll write the other one over here because I'll run out of room. Okay. Let's do the asymptotes. Again, asymptotes for x values between 0 and 2 pi. Basically, it's when this ratio does not exist, right? Or maybe I could just say I'll write it this way. And the only way that tangent of 3x does not exist is when cosine is equal to 0. So cosine of 3x equaling 0. So denominator is equaling 0. That's where we get the asymptotes. That means from last class period that my angle has to be like, again, negative pi over 2, positive pi over 2, 3 pi over 2, 5 pi over 2, et cetera, et cetera, et cetera. And then I'm going to divide everything by 3. Okay. Now, at the same time I do that, I'm also going to just look at the ones between 0 and 2 pi. So if I divide negative pi over 2 by 3, I get negative pi over 6. That's not bigger than 0. So I'll leave that one off. But when I divide pi over 2 by 3, I get pi over 6. That is between 0 and 2 pi. When I take 3 pi over 2, divide it by 3, I get 3 pi over 6, or you can reduce that to 1 pi over 2. I'll leave it at that right now. 5 pi over 6 is between 0 and 2 pi. 7 pi over 6 is between 0 and 2 pi. 8 pi over 6 is between 0 and 2 pi. 9 pi over 6 is between 0 and 2 pi. 11 pi over 6 is between 0 and 2 pi. If I went to 13 pi over 6, I'd be over 2 pi. Right? 13 over 6 is more than 2. So there you go. Basically what I'm doing, I'm just starting and ending above 0, ending before I hit 2 pi. So here are my solutions. And each one of those gives you an asymptote. Each one of those gives you a vertical asymptote. In this case. Any questions about how I'm getting those? So when numerator's 0, you get zeros. When the denominator is 0, you get the asymptotes. Let's do another. Let's do the 4 cotangent x over 2 minus 3. We'll start out with the amplitude. Goes from cotangent goes from negative infinity to positive infinity. So amplitude doesn't exist. Or again, some people would say the amplitude is infinite. The period is going to be pi divided by a half, because that coefficient is a half there, which is, by the way, 2 pi. We're going to have a horizontal shift. Well, it's going to be 3 over a half. Six units. So it's a positive 6. That's going to be 6 to the right. Are you okay with that? 3 divided by half. It's always the C over the B. B here is your coefficient of x. X over 2 is the same thing as half x. Yeah.
Would the C be negative if in the equation it was a plus?
Correct. Yep. Yeah, if that were a plus 3, then the horizontal shift would be a negative 6. Yeah. But it's always a bx minus c. And that minus c. So the minus c minus whatever this is affects it that way. So this would be a shift to the right. And then we have no vertical shift. Let's do the zeros here. Cotangent is cosine of the argument divided by sine of the argument. So we get zeros when cosine of x over 2 minus 3 is equal to 0. And again, just like we had last time, just like we have every time, that means our angle, if cosine is 0, that means our angle has to be pi over 2, 3 pi over 2, et cetera, et cetera, et cetera. On this one, you'll have to be careful. Our angle is x over 2 minus 3. So that's the thing that has to be equal to the negative 3 pi over 2, the negative pi over 2, pi over 2, 3 pi over 2, 5 pi over 2, et cetera, et cetera, et cetera. I'm going to have to add 3 to both sides. That means add 3 to all of these. And then I'm going to have to multiply both sides by 2. Or if you'd rather, you can multiply both sides by 2 now. You multiply both sides by 2, you get x minus 6 equals that times 2. So that gets rid of the denominator. Or you could add 3 to both all of these angles and then multiply by 2. You better understand what I'm doing there. So however you solve this, this is fine. I think I'll just multiply by 2 times everything on both sides first. If you want to add 3, you can add 3 to both sides first. If I multiply both sides by 2, all of my solutions on the right-hand side turn into negative 3 pi, negative 1 pi, pi, 3 pi, 5 pi, odd integer times pi, all those on the right-hand side. And then I'd add 6 to everything. Everybody see that? And just like I said earlier, if you wanted to, you could have added 3 first and then multiplied both sides by 2. You get the exact same thing at this stage, whichever way you do that. Now, one of the things, we wanted the zeros from 0 to 2 pi. If we're looking at the x values that are going to give us 0 between 0 and 2 pi, I have to take into account that 6. Like pi plus 6 is more than 2 pi. Does that make sense? I'm going to go back one. Just to emphasize something. If you type in negative pi negative 5 pi plus 6. That's less than 0, right? That's less than 0. What about negative 3 pi plus 6? Also less than 0, right? Negative pi plus 6, that is between 0 and 2 pi. But if you do pi plus 6, that's above 2 pi. That's above that, about 6.28. Okay. So the only value in this set, this entire set, that's between 0 and 2 pi is negative pi plus 6. So between 0 and 2 pi, we only have 1 0. That's the only value between 0 and 2 pi in that entire set. If we're looking for asymptotes, we're going to do almost the exact same thing we did there. We're just going to say, well, this thing can't exist. So that means the denominator has to be equal to 0. In this case, that means the sine has to be equal to 0. So the angle x over 2 minus 3 has to be something like integer times pi. And once again, we're at this stage where we can either multiply both sides by 2, or I can add 3 first. And then if I multiply both sides by 2, then I'd have to add 6. If I added 3 first, then I'd have to multiply both terms by 2. Both. Does that make sense? So same solving, I'll probably multiply by 2 first, giving me x minus 6 is equal to, we get a negative 4 pi, a negative 2 pi, 0, 2 pi, 4 pi. So even number times pi, and then add 6 to everything. By the way, negative 2 pi plus 6 is negative. Two pi plus 6 is above 2 pi. So the only number that is actually between 0 and 2 pi is just the number 6. So I'm just looking for asymptotes between x values of 0 and 2 pi. The only option is 6. It's the only asymptote between 0 and 2 pi. That makes sense? So this gives us all of our properties of tangents and cotangents, and the interesting parts of tangents are periods, shifts, where they have zeros, where they have asymptotes. Okay, the zeros are going to be the zeros of the numerator. The asymptotes are going to be the zeros of the denominator. So that's tangent and cotangent. That's the look of their graph. Secant and cosecant work differently. Remember, secant is like 1 over cosine. Well, 1 divided by cosine is going to have zeros. So we're going to end up with asymptotes where cosine is 0. But we're not going to end up with zeros with just our base secant function. Our base secant function never crosses the x-axis. It has a bunch of like U-looking shapes, both pointed up and pointing down. Same thing with cosecant, has a bunch of U-pointed shapes, pointed up and pointed down, that only get as low as 1 or as high as -1, depending on whether we're pointing up or down. Okay. By the way, let's just do a secant and let's compare that to cosine. See what's happening here? Cosine oscillates back and forth between -1 and 1. If I take the reciprocal of any number between -1 and 1, it's going to be in absolute value bigger than 1. Does that make sense? Like if I took the reciprocal of 1/2, it's going to be 2. Or the reciprocal of -1/4, it's going to be -4. So absolute value is going to be above 1. And the lowest points of those U-shaped curves are going to happen, of the U-shaped curves that are pointing up, the lowest points are going to happen at the peak of the cosine. And the highest points of the U-shapes pointing down are going to happen at the low point of cosine. Right? Where the cosine is -1. And at those places, notice the output of 1 has reciprocal of 1. So we're just doing reciprocals here. Okay. And then obviously where we cross, where we have 0, since the reciprocal of 0 is undefined, 1 over 0 is undefined, we get an asymptote there. So we get asymptotes of the zeros of cosines. And this is going to be the same relationship between cosecant and sine. Now, because we have parts of the U that are pointing up and parts of the u that are pointing down, we have to go through both u's to have a period. So we end up with a period of 2 pi on both of the secants and the cosecants. So secant, cosecant, sine, cosine all have periods of 2 pi, where tangent and cotangent have periods of pi. Right? Secant, cosecant, sine, cosine all have periods of 2 pi. The domain is not all real numbers because we have the asymptotes. The range goes from negative infinity up to -1, and then skips between, there's nothing between -1 and 1, and then starts back up at 1 and goes to infinity. All right? So we have this middle gap where our cosine is. Other than that, I can go negative infinity to infinity. Okay. And as we said, there are no zeros for these functions. We never cross the x-axis with secant and cosecant. The asymptotes happen when the denominator is 0. So in the case of secant, since secant is 1 over cosine, when cosine is 0. For cosecant, since that's 1 over sine, when sine is 0. By the way, secant is even and cosecant is odd. Secant is even because cosine is even. And it's just the reciprocal of cosine. Cosecant is odd because of the fact that cosecant is the reciprocal of sine. Does that make sense? We can go ahead and show that real quick. I'll do it over here. So if I took secant, for instance, and I plugged in a negative x, I can think of that as 1 over cosine of negative x, but we know what cosine, even and odd, does. Cosine is even, so cosine of negative x gives me just the same thing as cosine of x, which is the secant of x. So that's what I get when I plug in a positive number into my function. So secant is even, and for the same or similar reason, cosecant is odd. Since sine is odd, we pull out the negative sign. And when we pull out the negative sign, that becomes a negative cosecant, and therefore negative cosecant is odd. Or excuse me, that's a negative cosecant. Cosecant is odd. So the cosecant function is odd. The secant function is even because of the relationships to cosine and sine. Does that make sense? Good. All right, the evenness and oddness is not a huge deal. I just wanted to point that out. And then we can do our standard thing of shifting, stretching, flipping if we want, vertically stretch, horizontally stretch, all that good stuff to either my secant or my cosecant. What I have written on this slide is just the secant, but we could have just as easily done this to the cosecant. Once again, amplitude does not exist here because we can stretch out to positive infinity and down to negative infinity, even though we're missing that middle section between -1 and +1. But the amplitude does not exist. Some people would say amplitude is infinite again. Since B is our horizontal stretch or shrink, the period is now going to be adjusted by B. It's going to be 2 pi divided by absolute value of B. The horizontal shift, the phase shift is C divided by B. And then if we had a vertical shift, it'd be D. By the way, if we shift enough vertically, we could have zeros of a transformed secant function. Does that make sense? If we shift far enough up vertically, then all of those u's intersect the x-axis. But our base will have no zeros. Base function for secant or cosecant won't have zeros. Let's just do one of these. Let's take, I'll take g of x this time, okay? We've done a couple of them last time. This time we'll just do one of these. I'll do the second one. Cosecant of 3x minus 5. The 3x minus 5 all in parentheses. And we're going to do the same thing we did in our previous examples. We are going to find the amplitude, the period, the phase shift. No vertical shifts here. And then we're going to find the x-intercepts of the zeros and then the asymptotes. And when we do that, we'll find those x values which are between 0 and 2 pi. So let's just do that for the cosecant of 3x minus 5. What's the amplitude here?
No exist.
Does not exist. Exactly. Does not exist. Again, some people would say infinite. Period.
Two pi divided by 3.
2 pi over 3. Exactly. 2 pi over 3. We have a horizontal shrink by 3, so 2 pi over 3. Okay. The phase shift or the horizontal shift is going to be 5 over 3. And that's going to be a shift to the right. Okay, so we're shifting to the right 5 over 3 units or 1 2/3 units. Okay. There's no vertical shift. I won't even write that down. Zeros or x-intercepts. We're looking for zeros or x-intercepts. One way you can think of this is think of g of x as 1 over, in this case, sine of 3x minus 5. And you can ask yourself, when is the numerator 0? And it's never 0, right? So there are no zeros for this function, or no, that means also no x-intercepts. So no zeros. No x-intercepts. Okay. Now, if we're looking for asymptotes, again, we'll look for the asymptotes where x is between 0 and 2 pi. Again, I look at this function written as 1 over sine of 3x minus 5. And I know that the asymptotes are going to happen when the denominator is equal to 0. Sine is equal to 0 when we have integer times pi. So that means my angle could have been something like -2 pi, -1 pi, 0, +1 pi, +2 pi, 3 pi, etc., etc. And we're going to divide by 3 and add, well, let me rephrase that. Depending on what you want to do first, you can divide everything by 3 first, or you can add 5 first. If I add 5 to everything first, and then divide by 3, that's fine. If I divide by 3 first, then I'd have to add 5/3 to everything, because that would become there. I'm going to do both of those in just one step. That would become -2 pi over 3 plus 5/3. -pi over 3 plus 5/3. 0 plus 5/3, which is just 5/3. Pi over 3 plus 5/3. 2 pi over 3 plus 5/3. 3 pi over 3 plus 5/3. And then I just keep going and going and going. Okay. I want just the x values between 0 and 2 pi. So I'd probably just type things in. If you type in -2 pi over 3 and add 5/3, this is a negative number. If you type in -1 pi over 3 and add 5/3, that's positive. So we're going to start right here and go out for a while until we hit something that's above about 6.28. if I take 3 pi over 3 and add 5/3, I get 4.8. So I need to actually go out further than what I've already written on the board. Where's mine? There it is. So we're going to go out a couple more. 4 pi over 3 plus 5/3. 5 pi over 3 plus 5/3 plus 5 over 3. That makes sense. This gives me about 5.86. When I take 5 pi over 3, I get 6.9. That's above 2 pi. That's above 6.28. So I can stop here. So those are the answers of the asymptotes between 0 and 2 pi. That makes sense. I just keep going out until I get something above 6.28. Once I get something above 6.28, I say stop. Everything before that. And you'll probably actually round these numbers to 2 decimal places anyways when you do something in Moodle. So I know I'm writing the exact answers, but in Moodle you'll probably have to round things to 2 decimal places. Stop. So those are all the x values between 0 and 2 pi that give us asymptotes. Any questions about that? Straightforward. Good. Now, I've already kind of been talking about this throughout. The evenness and oddness of trig functions. And I just wanted to talk about vertically stretching things, horizontally stretching things, and then vertically and horizontally shifting our trig functions and what that does to the evenness and oddness of a function. If I vertically stretch something, it's going to stay even if it's already even. If I vertically stretch something, it's going to stay odd if it's already odd. Same thing with a horizontal stretch. If you think about that, we're just stretching away from either the x-axis if we're vertical, or the y-axis if we're stretching and shrinking horizontally. Does that make sense? So stretching vertically or horizontally keeps the evenness or the oddness of a function. So if I stretch a sine function, stretch a tangent, stretch a cotangent, stretch a cosecant, those are all going to remain odd. And the same thing is true with cosine and secant. If I stretch those, they'll stay even. But vertically shifting things and horizontally shifting things does not necessarily keep the evenness and oddness of a function. Okay? Usually it doesn't unless it's shifted in the real precise way. Okay. Does that make sense? So if I look at these, functions, cosine of x over 2, well, that's just a cosine function stretched horizontally by a factor of 2, so that's still even. Tangent h of x, oh, we didn't have anything. There's no stretch there at all. That's still odd, I guess. Not very even interesting, is it? Secant, that's going to be, well, that's 1 over cosine, so that's still even. Right? That's just a stretched out secant, still even. But here we have a shifted tangent. That's going to be neither even nor odd. We shifted it over 2 units. Tangent has a period of pi. If I would have shifted it over pi units, I would have gotten something. Does that make sense? But shifting it over 2 units, that loses the evenness and oddness of these trig functions. Okay, unless I shift it by a factor of pi, it's not going to work. You can also combine functions. Now that I have trig functions, I can combine those with polynomial functions, which I know are even or odd. Remember talking about even and odd polynomial functions back in the day? What's x squared? Is that an even or an odd polynomial? Well, if you square something, it gets rid of the negative part, right? So that's even. And x to the third is an odd polynomial. So here what we have is a function f of x, which is 6x squared plus cosine of x. That's even plus even. You're adding together 2 even functions. Whenever you add an even plus an even piece, the result is also going to be even. So 6x squared plus cosine of x is also even. Let's do a k of x next. Here we have an odd x to the third and an even secant. When you add an odd plus an even function, we have 2 pieces. One piece is an even piece, another piece is an odd piece. That's a neither. Does that make sense? Now you can do this algebraically if you like. If you like, you can just plug in a negative into our function k of x. And see what happens. Remember, this is how we tested algebraically. If things were even or odd, we plugged in a negative. If we got back the original function, we knew it was even. If we got back the opposite of our original function, we knew it's odd. In this case, we'd end up with negative x to the third plus a secant of x. We do plus secant because secant's even. We already established that. This is neither the original function nor the negative of the original function. This is not k of x and not negative k of x. So this one is neither even nor odd. In that case. If I would have done that same algebraic approach with our first function, which was x squared plus cosine of x, if I would have plugged in a negative, I would have ended up with an x squared plus cosine of x, which is my original function. And therefore, we could have said algebraically that guarantees it's even, right? Okay. Yeah.
Just like, say we just typed in -5 and put that on, and we got the same answer, would that also work?
You wouldn't want to do it, you'd have to do it with any value of x. So specific values may give you out. It might just by circumstance, but if you used a lot of values, you'd see that they either all are going to work or they're all not going to work. If that makes sense. But so you have to do it for an arbitrary x value for all values of x. By the way, this is kind of like negatives and positives. If you think about evens, they kind of work as positives. Negatives kind of work as odd functions. If you add in even plus an even number, or no, excuse me, positive plus positive number, even plus even function, positive plus positive, you're going to get out a positive, right? Here we're saying, well, we have a negative number and a positive number. Well, sometimes those will add to negative, sometimes those add to positives. It's indeterminate. Then you look at something like g of x. Here we have an odd function divided by an even function. We have sine over x squared. That's an odd function divided by an even function. Any guesses whether this would be even, odd, or neither? Neither. Turns out this one is odd. It's kind of like when we had sine over cosine. Cosine was even, sine was odd. If you plug in a negative x, you can bring the negative out front of sine, but if I plug in a negative x in the denominator, the negative is going to go away. So I'm going to get one negative I can bring out front of the whole thing. They follow that? So it's kind of like a negative number divided by a positive number always has to be negative. You can algebraically compute that too if you'd like. I'm not going to do that one. Like negative over positive gives you a negative always. And in a similar way, this last one, h of x, which is tangent times sine, We know that tangent is odd. We know that sine is odd. If I multiply an odd function times another odd function, I get an even function. Kind of like the way negative times negative gives me a positive. Can you follow that? So h of x is going to be even because it is the product of two odd functions. The g of x was odd because it was the quotient of an odd function with an even function. When in doubt, plug in a negative x and see what happens. Okay. When in doubt, plug in a negative x, see what happens. If you get the function back, then we know we have an even function. If you get the opposite of the function, we know we have an odd function. And if you get neither the exact function value or the opposite of the function value, then we're in the neither case. So that's the end of sections 6.1 and 6.2. Now, the last section we're going to cover in chapter 6 is section 6.3 on inverse trig functions. So our trig function is such that we're inputting an angle and we're getting out some trig operation of the angle. So like a trig function like cosine, we input the angle of theta and we get out the cosine of theta, which is related to some point on the unit circle, the x value of a point on the unit circle. Now what we're going to do is we're going to reverse that operation. We're going to start with the x value of a point on a unit circle, and we're going to get back the angle. Okay. So that's what the inverse does, or specifically the inverse of cosine does. Inverse cosine of an x value is going to give me back some angle. Inverse sine is going to be, I'm going to put in something into that function, which is going to be the y value on a unit circle, and I'm going to get back an angle. Now the trouble is that inverse functions, as we saw when we were way back in unit 1, come from one-to-one functions. And we know that sine and cosine are not one-to-one. All right? They're periodic, so we have this repeating pattern. So they're not one-to-one. And that's because of coterminal angles. And there'll be one other thing in a second. So because we have these waves in our cosine and sine functions, we're going to have to force ourselves to look at just one section. We're going to have to force ourselves to limit the domain of cosine and sine so that it's one-to-one. And then we can limit the range of the inverse properly, or we can get inverses properly. So here's what we do. We take the cosine function, since the outputs range from -1 to 1. Let's see if we're good. I'll do that. We're going to start it here and go all the way out to here. Notice that's not even a full wave. That's just basically a half of a wave. So to limit, so we can have an actual inverse, we're going to limit the x values from 0 to pi. Or actually, we're going to limit the angles we input from 0 to pi, and therefore the angles that we input that we get out of the inverse. So angles you input into cosine and the angles you get out from the inverse of cosine are going to be from 0 to pi. Okay. If I tried to do that with sine, I would not get 1 to 1. See that? It still failed the vertical, this means failed the horizontal line test if I went 0 to pi on sine. So for sine, what I have to do is I have to start at -pi/2 and end at a +pi/2. For my inputs of sine, that would be my outputs of the inverse. So the outputs of the inverse are going to be from -pi/2 to +pi/2. That all make sense? Hopefully. Okay. So we got to limit the domain and range for this whole thing to work. For us to have inverse functions, we have to limit the domain and the range. Okay. You can also view this via the unit circle. Cosines are the x values on this unit circle. So for cosine, in order to get all the x values, we'll start here and we'll go all the way around to here. We'll go from 0 to pi. So we'll have the top half of the unit circle. Okay. If I did that same thing for sine, if I started here, we'd only get positive y values. So that's not going to work for sine. So cosine, you have to use the top half of the circle, essentially. For sine are y values. So what we're going to have to do is we're going to have to go to the lowest y value around the unit circle until I hit the highest y value. So I'm going to only be dealing with the right-hand side of the unit circle from -pi/2 to +pi/2. Did you get that? So whichever way you want to think of it, we can do that. Now, this unit circle also tells us, if we want to, how to calculate inverse cosine and inverse sine by hand. Okay, so if we want to do this by hand for specific values like √3/2 or 1/2 or √2/2 or 0 or 1 or -1 or -√2/2, we can actually do that via unit circle if we want. Okay. But these are the restrictions. Inverse cosine, the range of our outputs are going to be from 0 to pi. For sine, the range of our outputs, inverse of sine is going to be from negative pi over 2 to positive pi over 2. That's the big thing. We're restricting our range for inverse sine and cosine. And that in turn restricts the inputs for cosine and sine that we can use. Now, one other thing before we start calculating stuff. Inverse cosine has another notation, which is arc cosine. So the arc cosine and inverse cosine, both, we're putting in an x value on the unit circle, and it's giving me back an angle. Okay. There are some weird distinctions between them. All right. In this class, we use those notations interchangeably. So in really high level mathematics, those notations can mean something slightly different. But in our class, we use those interchangeably. Okay, so those are interchangeable notations for this class. And the same thing with sine inverse and arc sine. So if you ever see arc sine or sine inverse, they mean the same thing for our class. Okay. Now for our tangent, we've done sine and cosine. It turns out that tangent works best when we limit the inputs of tangent to negative pi over 2 to positive pi over 2. And so when we do an inverse tangent, our outputs are going to be from negative pi over 2 to positive pi over 2. So tangent works with the same range and domain as cosine. And once again, notationally, we can have arctangent instead of tangent inverse. So arctangent or tangent inverse are interchangeable for us. Okay. And if you want to, you can do inverse of secant, inverse of cosecant, inverse of cotangent. Those we don't really have to deal with a whole lot because we can always algebraically manipulate cosine, sine, and tangent through reciprocals to figure out secant, cosecant, cotangent. So in the same way, to do inverse secant, we can write everything as cosine and take an inverse cosine of something. To do an inverse cosecant, we can write everything in terms of sine and then take an inverse sine of something. To do inverse cotangent, you can do inverse of tangent of something else through reciprocals. So usually we focus on the cosine, the sine, and the tangent ones. And then the others, we kind of just say, yep, we could do those too if we wanted to. Now, like I said, we could trace this around on the unit circle, and we could use the unit circle to find inverses or of sines and inverses of cosines of distinct values. So let's look at the sine inverse of root 3 over 2. Let's look for that on the unit circle. We'll do this by hand first. And then sine inverse of negative root 3 over 2. We'll do the arc sine, which is the same thing as sine inverse. So arc sine of a positive root 2 over 2. And the arc sine of negative 1/2. Now I've written all these on the board. What I'm going to go back and do is I'm going to go back and look up what angles give me that y value on the unit circle. What angles between negative pi over 2 and positive pi over 2, give me that on the unit circle. So let's start with sine inverse of root 3 over 2. Sine on the unit circle is my y values of the points. So what I'm looking for is a y value that is root 3 over 2. That's this one right here. You see that? That comes from the angle in radians, which is pi over 3, or in degrees, which is 60. We'll use radians for everything. So the inverse sine of root 3 over 2 is the angle pi over 3. Are you okay with that? Now I want you to notice that there was another angle that gave us a y value of root 3 over 2. But we limited ourselves with our inverse to just the right half of the circle. Remember that? So with our inverse sine, we were limited to the right half of the circle. And so this one, we didn't account for at this point. Does that make sense? Let's go to the next. The next is sine inverse of negative root 3 over 2. So sine gives us out y values. We're on the right-hand side of the circle. We're looking for a y value of negative root 3 over 2 on the right-hand side of the circle. That's this. Oops. See if I can make this bigger. No, I can't do that. If I can do this. Gotta be a big way to do it. There's probably some way. But y value of negative root 3 over 2 is this one. Now you have to be careful here. On this picture of the unit circle, it says 5 pi over 3. We're supposed to get out values between negative pi over 2 and positive pi over 2. So that's technically negative pi over 3. Does that make sense? Because instead of swinging all the way counterclockwise, we want to swing clockwise down there. So just take 2 pi, subtract 5 pi over 3. Actually, I misspoke. 5 pi over 3 minus 2 pi, we get negative pi over 3. Does that make sense? Think coterminal angles. So five pi over 3 minus 2 pi negative pi over 3. Okay. Any questions about that? We're doing this. I want you to take that picture and try to do the inverse sine of root 2 over 2 and the inverse sine of negative 1/2 using that picture. I'll share that on the board too. Write your answers in radians between negative pi over 2 and positive pi over 2. Since we're dealing with arc sine. All right, with the first one, arc sine of root 2 over 2, we're looking, root 2 over 2 is right there at pi over 4. So pi over 4 is the answer for arc sine of root 2 over 2. Okay. Arc sine of negative 1/2. Well, negative 1/2 as the y value is right here. That would be 11 pi over 6 if I went around in the counterclockwise direction. That would be negative pi over 6. In the clockwise direction. Okay. Since I want my angle to be between negative pi over 2 and positive pi over 2, it's going to be a negative pi over 6. Okay. Now, if we did a similar thing with cosine, or tangent, we'd have to be conscious about how we looked at the circle. So let's take inverse cosine of negative root 3 over 2 and arc cosine of 1/2. And then do an inverse tangent of the square root of 3. And then we'll do an arc tangent of 1. Okay. So on this unit circle, when we're looking for inverse cosine, cosines are the x values of those points. So when I see inverse cosine of negative √3/2, I'm going to find when the x values are negative √3/2. There's one here on the bottom half of the circle. There's one here on the top half of the circle. Since inverse cosine only deals with the top half of the circle, we're using that one. Everybody see that? So the inverse cosine of negative √3/2 is the angle 5 pi/6. 5 pi/6. Can't see. If I do arc cosine of 1/2, again, I look for x values on the unit circle. Here's an x value on the unit circle that's a half. Here's another x value on the unit circle that's a half. Because cosine only deals with the top half of the circle, I have to use this one. So that's pi/3. Arc cosine of 1/2 is pi/3. Now, it's tougher to see inverse tangent on the unit circle, okay? Because tangent is the ratio of these 2 points. Does that make sense? So when I look at inverse tangent of √3, I have to look at the ratio of those, the y value over the x value, sine over cosine. Right? So I need the y value of the point to be √3 times the x value of the point. Does that make sense? So the thing I need, didn't draw very well. The thing I need is the x value to be 1/2 and the y value to be √3/2. By the way, notice that you get the exact same ratio down here because the negatives would cancel out. But inverse tangent just uses the right-hand half of the circle. So we ignore the one on the left-hand side of the circle. So inverse tangent of √3 is also pi/3. How about arctangent of 1? What ratio do we need between the y and the x to get a 1? Go ahead. Yeah.
Wouldn't pi/4 make the 45-degree angle work, since if they're over each other, it just becomes 1?
Exactly. Yep. So the 45-degree angle, √2/2 divided by another √2/2 gives me the ratio of 1. In other words, my x value and my y value are the same. So the ratio of 1 comes from the x and y value to be the same. A lot of people get thrown off by that, but ratio of 1 means the x and y are the same. So we're getting pi/4 as our angle in radians. So we found exact values. Oh, shoot. Hit the wrong button. There we go. So we found exact values for all of these. Okay. Now, not every value we plug in is going to be on the unit circle. Root 3 over 2, 1/2, root 2 over 2, those were special values that we saw on our labeled unit circle. But if I said find the inverse sine of 0.3, 0.3 is not an y value on the unit circle that I've labeled. So if I don't have nice inputs, what I could just do is turn to the calculator. In fact, I could have probably turned to the calculator with the ones I've written on the board as well. And the nice thing about our calculators is that when we do inverse sine, when we do arc sine, and we type that into our calculators, it'll give me out values already between negative pi over 2 and positive pi over 2. That's just the standard for any inverse sine. And for any inverse cosine, it'll give me values between 0 and pi. So let's do that with a few of these. I'll just show you on your calculator. Sine inverse negative 0.41. And then arc sine 0.92. And then it says arc sine of negative 1.25. Okay. Oh, shit. Wait, turned off the camera. Hold on. Well, probably don't need that. In a second, it will. Yeah, that'll do that. If it works. I'm seeing it. It's not projecting. Okay, there we go. Now I'm back. Now, this is the same inverse feature we did with triangles, so it shouldn't be any new feature to us. So inverse sine is just second into the sine button. We want to do negative 0.41. So that's what it looks like, inverse sine, negative 0.41. So bring this way up. Hit enter. Now, why did I get negative 24.20? Rather, that's probably negative, not negative 24.20 radians. That's a lot of radians. That's because my calculator right now is in degree mode. Okay, so make sure in this part, when we're graphing, if we want things to be in radians, make sure your mode of the calculator is in radians. And we do want our, essentially everything except for triangles we use radians with, okay, for the most part. For the most part, triangles we use degrees. Anytime we're graphing, we use radians. If I want to do arc sine, that's just, again, for our class, the same exact thing. So if you see arc sine of 0.92, you could have just did that. Okay. By the way, we could have also done that for something that we saw earlier, like root 3/2. If I wanted to do arc sine of square root of 3 divided by 2, I could have just typed that in. I get a decimal version of pi over 3. So this is just the decimal version of pi over 3. Sometimes that's easy to recognize, sometimes that's hard to recognize. So if you wanted exact values, that's another way to do it. Just do inverse sine and see if that's like pi over 3 or pi over 6 or pi over 4 or whatever you want it to be. Everybody okay with that? So inverse sine, arc sine. Now, one thing to watch out for, if you do inverse sine of something like negative 1.25, this would also happen if you did 1.25. What you're going to get is an error because the sine was the y value on the unit circle. For on the unit circle, that means our lowest value that we can input into inverse cosine is -1, and our highest value that we can input to inverse sine is a +1. They get that? So our domain goes from -1 to +1 because that is how far the unit circle stretches down and up. The same thing will be true with cosine. When you input if I input cosine inverse of something that was bigger than 1 or less than -1, it's going to give me a domain error because unit circle goes from -1 to +1. Okay. Does that make sense? So we can, as long as we're careful that we're in radian mode. Keep hitting the wrong button. We're good to go on inverse sine and cosine. Okay. By the way, tangent does not have that problem. So, for instance, if I wanted to do arctangent of 2.25, tangent is the ratio between the 2 points, and that ratio can go from -infinity to +infinity. So inverse tangent of 2.25 will actually give me an answer out. It'll give me about 1.15. Does that all make sense? Good. All right. We're going to stop here. And next time we'll pick back up with solving trig equations using these inverse features. Okay? So that means we're not completely done with section 6.3. So I'll put section 6.3 homework back till not this Friday, not tomorrow, but the next Friday. But make sure you get done with the end of chapter 5 and the 6.1, 6.2 homeworks by tomorrow at 5. Okay? All right. I'll see you then. See you next.